Hi, my name is Pascal Poupart, and in this module I will give a brief introduction to distributional reinforcement learning. Distributional reinforcement learning refers to the fact that we won't be modeling just the expectation of the rewards, but the full distribution over the rewards. There are several reasons for doing this, and one of them is simply that we can enable or define new types of objectives that are risk sensitive. So if we don't model just the mean, but we consider the full distribution, then we can consider other statistics like the variance, and then we could try to minimize the variance or other notions of variations in the rewards. To do this, we'll need to define some distributions over the returns and see how to do the computation with that. And then in the end, we'll discuss one basic algorithm known as C51 or Categorical DQN that was proposed by Bellman et al. In 2017. Let's look at the objective in reinforcement learning. To do this, we're going to denote Z as a random variable, and it's going to correspond to the sum of discounted rewards, where the rewards themselves are also random variables. Now, in traditional reinforcement learning, the objective is to maximize expected rewards, which really correspond here to the expectation of Z, or if we prefer, the mean of Z. We can also consider other objectives that are going to be risk sensitive in the sense that they can take into account other statistics from the distribution of returns. So for instance, we can consider the mean variance objective, where we maximize the expectation of Z minus a multiple of the variance of Z. Alternatively, we can also consider the cumulative distribution. So that is the probability with which Z would be less than or equal to some threshold small z. So if we pick a threshold, then the idea is that we would like to minimize the probability that any of the returns are going to be less than that threshold. Another possibility is to consider value at risk. This is a risk measure that was defined in finance, and it really just corresponds to the inverse of the cumulative density function with respect to some threshold alpha. So normally the cumulative density function has a threshold which is Z, so that's a value for the returns. But if we take the inverse, then instead we take a probability as a threshold, so like alpha could be 10%, and now we would like to maximize what is the largest value that would still be within 10%. Another possibility is to consider conditional value at risk. So this is also from finance, and the advantage of this one is that now we don't just consider a threshold, but we can still do an expectation with respect to the quantities that we care about. So here we'd like to maximize the expectation of the Z's, but only the Z's that are greater or equal than the value at risk for some threshold alpha. So what is common to all of those objectives is that we need to rely on the underlying distribution of returns. So on this plot here, I've got an example of a distribution. So it's just an arbitrary distribution, and you'll notice that it's in terms of our random variable Z, and then the y-axis here indicates the probability that each one of those returns occurs. So now given this distribution, then we can compute all sorts of statistics and compose in this way our favorite objective. Let's look at the return distribution in more details. The return distribution corresponds to this variable Z, and it is the sum or the discounted sum of the rewards, but really here we have an arithmetic expression in terms of several random variables. The most obvious one is the reward variable, so that comes from our reward distribution, but then you'll notice that it depends on the current state and action pair, which are themselves random variables. So the state at a current time step depends on the state at a previous time step according to the transition distribution. And similarly, the action is a random variable, so it is sampled from the policy under the assumption here that the policy is stochastic. So really, we can think of Z as a random variable that is composed of some arithmetic operations over several random variables. Now, when we do traditional reinforcement learning, what we're really doing is to maximize the expectation of this random variable, and that's what we call here the value function, right? So the value function is just this expectation with respect to those three distributions that we discussed here of the discounted sum of rewards. In practice, when we evaluate a policy, we don't do it just by summing up all of the rewards over the planning horizon. Often what we'll do is take a recursive definition based on Bellman's equation, where we sum the current reward plus an expectation over the future rewards that are gathered into the current Q estimate. So policy evaluation is really here an expectation over all of those random variables, but written into a recursive form. And the same recursive form for the random variables would be just that we define Z to be the current reward R plus the discount factor times the random variable that corresponds to all the future rewards. Now, there's a big distinction between those two equations, right? So the first one is a regular equation in terms of numerical values, whereas the second one is really an equation in terms of random variables, and that behaves differently. So let's illustrate how this works. So if we start with the random variable of the future rewards, so Z of S prime A prime, we can represent this by some distribution like this. Then when we multiply that random variable by gamma, what happens is that the domain will shrink. That's what we observe here. And then the probability of each one of those values will possibly go up, right? So that's the effect here of multiplying a random variable by a discount factor gamma. Then after this, when we add the reward variable, this is another variable, but now just for the sake of this example, if we assume that the reward is a constant, if we add a constant to our current distribution, you see it will simply shift by that constant. So essentially the support just shift towards the right in this example. And more generally, if the reward was a random variable, then we would take the convolution of those two random variables, which would give us a new distribution. So that's how we have to think about these equations in terms of random variables. We can study the convergence of this policy evaluation approach with respect to the random variable Z. So here you see, since Z is a random variable, there is really a distribution, and then when it converges, then it should converge towards some fixed stable distribution. To study this, we're going to define an operator T with respect to a policy pi, and the idea is that when we compute R plus gamma Z, we are essentially computing an update to the random variable that corresponds to the value of this policy, and there is a corresponding distribution for this. Now we're going to let T pi be this operator that does this update. So it turns out that there's a theorem similar to policy evaluation that's with respect to the mean that shows that this operator T pi will converge to a unique return distribution. Now the proof for this is beyond the scope of this course, but very briefly, the idea is that we can show that T pi is going to be a contraction mapping with respect to the Wasserstein metric. So the Wasserstein distance is a popular metric to measure the distance between two distributions. So here, if we measure the distribution before we do anything to two random variables Z and Z prime, and then after that we apply the operator T pi to those two random variables, then what we can show is that the distance between those two distributions with respect to the Wasserstein metric will be smaller than the original distance by a factor of gamma. So over time, you see, when we do policy evaluation, what happens is that we get an estimate of this random variable. It gets updated, but any error in the estimate will shrink over time due to this contraction mapping, and then this will ensure convergence towards a unique distribution, so a unique random variable. We can also write down a distributional version of Bellman's equation. So if you recall, Bellman's optimality equation in terms of the Q function would simply be the expected immediate reward plus the discount times an expectation of the future rewards, assuming that we always select actions greedily afterwards. Now, when we write this in terms of random variables, we have a similar expression, and really all we're doing here is just dropping all the expectations. But then again, this equation being in terms of random variables means that it doesn't correspond to just a single value at the end, but it corresponds to a distribution. Now, what's interesting is that we cannot replace this argmax operator with arbitrary risk-averse objectives. So it turns out that when we consider the traditional objective of maximizing expected rewards, then the maximum over the sum of the rewards can be distributed in terms of a maximum over the rewards that we compute at every step. And overall, this ensures that the sum of the rewards is going to be maximum. But if we consider, let's say, not just the expectation, but also the variance, the problem is that if we have an expression that maximizes, let's say, mean minus variance at a certain time step, that might not be the best outcome for the next time step. And as a result, we cannot apply dynamic programming. So a lot of the risk-averse objectives don't lend themselves well to dynamic programming. In other words, we cannot compute gradually, step by step, what might be the optimal choice. So some suboptimal choices might be needed at some time step in order to ensure optimality at later time steps. And then so this is one of the drawbacks that prevents us from necessarily working with Bellman's equation. If we stick to maximizing expected rewards, then we can ask whether this Bellman operator in terms of distributions will converge to a unique distribution or not. And unfortunately, we have a negative result here where we can show that the optimal return distribution is not unique. So what happens intuitively is that we know that there might be several optimal policies, and then each optimal policy might have a different optimal distribution. And naturally, you see, even though these optimal return distributions are different, they will all have the same expectation, so the same mean that correspond to the optimal value function. But unfortunately, the return distributions themselves, you see, are not necessarily unique. That being said, we can show that the operator T star will converge to a set of optimal return distributions. It's just that it's not going to be unique. It might cycle between these return distributions, but it will converge to one or several of those distributions in that set of optimal return distributions. Now, the proof for this is complicated, so it's beyond the scope of this course, and part of the complication is that we cannot show that the operator T star is a contraction mapping. Let's have a look at a particular algorithm, so a basic algorithm for distributional reinforcement learning when we maximize the mean. So this algorithm is called C51, and that corresponds to a categorical version of the DQN algorithm. So just to start, as a brief review, I've got here a picture of the DQN algorithm. The idea is that let's say that we apply it on some domain where the inputs are images, then there would first be a feature extractor, and then finally the Q network would have an output layer that would produce a vector, where this vector would consist of different values that correspond to the returns for different actions. Now we can compare that to categorical DQN, where it will do something very similar. So let's say it takes again a state as input, perhaps in the form of an image. Then there's a feature extractor. But now the main difference is that the output layer instead of producing a vector, is going to produce a distribution. In fact, it's going to be several distributions in the form of a matrix of softmax. So if we have, you see, a bunch of actions, now for each action, there's going to be a distribution over the possible returns, and that's what's indicated here. So you see in blue, we've got one distribution for the first action, in purple, another distribution for the next action, and so on. So the idea is that the C51 algorithm will work in a similar way as DQN, but the output of the neural network will be this matrix that correspond to a set of distributions, return distributions, one for each action. This slide summarizes the pseudocode for the categorical DQN. Now, because it is simply a variant of the regular DQN, we can see that the first part is really the same as before, and what has changed is what I highlighted in red down here. Now recall that the categorical DQN algorithm needs to output a distribution over return values, and then as a result, here we're going to define an interval in which we're going to project those values. So Zmin to Zmax is going to be the interval, and then we're going to discretize it into n grid points that have a space of delta z in between each one of them. So it's an equally spaced set of grid points from Zmin to Zmax. Now the distribution network is going to be denoted by Pw of z of sa equals zi. So that tells us the probability. So this network is going to return a probability that the return is equal to a specific grid point zi. This network now is going to be updated, and when we update it, what we're really doing is updating the probabilities that we're going to denote by pi. So pi are going to be those probabilities that we update and eventually serve as a target to train our distribution network. So the way this works is that we start with all the grid points, and then we compute updates for them by multiplying by gamma, adding the current reward. So that gives us now some new values, new return values, but these may not be exactly on grid points. So we're going to have to interpolate them, and the way we do this is that we find the index of the grid point that is right below. So that's, we're going to call this index L, and then the one that's right above, so this will be U. So with those two grid points, then we can take the probability of our grid point that we're currently backing up, and then simply distribute that probability between the one for the one below, so that's L, and the one above, which is U. So that's how we do the updates. So we end up at the end with a bunch of target values, pi, and then we can minimize cross entropy in order to train our network. So you see here our network again is denoted by Pw of zsa equals zi. So then this is the main difference with respect to a Q network, right? So here the objective will simply be cross entropy. And then as in regular DQN, we could use two networks, so that's why there's one that's denoted by W, that's the one we update at every step, but then we also have a target network that's denoted by W bar, and then we simply update the target network once in a while. You may wonder, what is the advantage of categorical DQN over regular DQN? So we saw that categorical DQN is maximizing expected return, but then in doing this, it's actually maintaining a full distribution with a more complicated update. But really, if we're just maximizing expected return, why don't we stick to regular DQN? That is obviously a lot simpler. So what's the advantage? It turns out that we can think of categorical DQN as really computing some form of weighted ensemble of returns. So if we look again at the equation for the expectation, when we work with the distribution of returns, so we're taking a weighted sum, and the idea is that if we have errors in the returns or their probabilities, then these errors may cancel each other when we take this expectation. So this is the same principle as ensemble learning, where you have several estimates, and then sometimes you see you have errors in one estimate, errors in another estimate that are that may cancel each other, and then overall you see with the ensemble you can typically get something that's more accurate. So this is more or less what's happening with categorical DQN when we just stick to maximizing expected returns. Categorical DQN was demonstrated by Bellman et al. In 2017 on the Atari benchmark. So we have here 5 games that shows the average score that is obtained with different number of grid points. So here 5 returns indicates that we have 5 grid points, 11 returns that's 11 grid points, and so on, up to 51 grid points. And naturally, the more grid points we have, the more precise is the distribution, and therefore the better the results are going to be. From an ensembling perspective, it also means that we might have more cancellation of errors, so that tends to produce better results as well. Now, back in 2017, what made categorical DQN really interesting and a lot of people paying attention to the algorithm and the ideas was the fact that it did improve the state of the art on the Atari benchmark. So this graph here shows all 51 games from the Atari benchmark. We've got on the y-axis the improvement in log scale with respect to the previous state of the art, which was double DQN. So we can see that for the vast majority of the games we have a nice improvement, and that just shows I guess the effectiveness of the approach. So following that, a lot of people define some improved version still based on distributional reinforcement learning, and in fact there was a series of new state-of-the-arts that were established by different distributional reinforcement learning techniques. One way to improve categorical DQN is to improve the representation of the return distribution. So if you recall, the C51 algorithm is really just using a categorical distribution which correspond to a set of grid points. Now the next thing to try is to allow those grid points to vary by using some samples, but then in a different direction, a lot of researchers started to explore the representation in terms of the quantile function. So here the quantile function is really just the inverse of the cumulative density function. So if you have the quantile function, you implicitly have the return distribution, and you can do all the computation with the quantile function. But the advantage is that from a statistical perspective, we can do quantile regression, which is much more effective than regular regression. The issue is that in regular regression, we need targets, and when we're trying to estimate a distribution, we don't usually have accurate targets. What we have are samples, and perhaps from those samples we can construct a probability, an estimated probability as the target, but that's not accurate. It turns out that there's a way to use those samples more effectively in terms of estimating the quantile function, and that has led to improved results. Okay, so I'm going to stop here, and I thank everyone for listening.